going to do today is take a look at what we call the complex number system. And to make it easy on you, think about the complex numbers as numbers that involve real and imaginary numbers. Real and imaginary numbers are the complex numbers. So what we're going to see, and if we think back to our tree diagram earlier this year, we talked about real numbers being here, and then real numbers broke into rational and irrational, and we talked about there's this whole other set called imaginary, and I said don't worry about that yet, we're going to talk about that. Well, the complex number system is the combination of these two. Okay, that's where it comes from. So the complex number system is a number set that includes the subsets of real and imaginary numbers. Okay, so there's going to be what's called the real component, and we're going to call that A. And you'll see that's already written on here. God bless you.
Sorry.
It's all right. Where A and B are real numbers, A is called the real part, and B is called the imaginary part. Okay? Again, A is the real part, B is the imaginary part. And if you guys remember yesterday, I quickly talked about how with electrical engineering, you have two parts of the solution, and these two parts, the real and imaginary part, will dictate the type of feedback in a system. So we talked about the example with cruise control real quick, and that's the idea here. The value of the real and the imaginary parts affect the type of result the cruise control system has, or what the cruise control does, whether it speeds up or slows down, okay, or the feedback in an electrical circuit as well. Okay? So we're talking about two parts of this system today. The complex number set, which is comprised of the real and the imaginary number sets. Okay? And in standard form, this is the way you're going to be writing it all year. Okay? This is your standard form of a complex number. A plus BI. Okay? So if you got an answer and the answer was this, okay, you're going to write it like the following. So A is 3/4 and B would be 17/4. So you can identify what A and B are. And you're actually doing this for a reason. It's not for no apparent reason at all. Okay, but when you identify A and B and you know the real and the imaginary component, those things alone can dictate what kind of a system you have. Okay, you might not see the applications as much this year in just math, but if you go on to study science or engineering, you'll definitely be using these components, the real and the imaginary component. And please remember, the real part is A, the imaginary part is B. The I just indicates that this whole thing is imaginary, or the whole thing itself is complex. But the 17/4 is called the imaginary part, even though the number 17/4 itself is real. Kind of counterintuitive there. Look at an example of this. Okay, let's simplify these two expressions. And for this, do it yourself. This should be very easy. The rule is combine like terms. Go ahead and combine like terms and see what you have. Remembering for part B that subtraction is defined as adding the opposite. Chris, first part A? Yeah. Again, the 2 and the 3 combine to give you a 5, 4i and negative 5i combine to give you negative 1i. Okay? Pat, part B. How can you rewrite it to make it easier?
6 plus 2.
Okay, so you're thinking about that. But let me just write it like this first. So then you're going to say plus 2, good, and plus 4i. So remember that you distribute the negative sign here. Now you have a minus 2 though on a negative, so this should be a minus in front of it. Okay, take a look here. See this minus here? And it's a positive 2. So when we distribute the negative, this is going to become a minus. And then when we distribute the negative, that becomes a positive. And then combine like terms, what do you get? Good. Okay, so this is absolutely no different than adding variables. Is that clear? So when you're adding and subtracting complex numbers, treat them identical to variables or treat them analogously to variables. Exact same rules apply there. But when you're multiplying and dividing, we're going to see some exceptions here. Okay? Second example now. Multiplication. Your rule here is treat it like FOIL. Okay? Treat it like it's foiling. But you have to remember the definition of I. We said that the definition of I was the square root of -1, which led us to the fact that I squared is just what? Joe? -1. Okay, please remember this component right here. Because you're going to get an I squared at some point along the way. Because you're foiling here. Remember, you're foiling, where you're double distributing. So when you get I squared, please replace it with -1. Go ahead and work through part A. If you finish, go ahead and B and C. For part B, think about the fact that you're squaring it, but you have to FOIL still. For part C, try and notice something and think about radicals for part C. Try and notice the correlation that exists between this and radicals. Show of hands for part A. How many people have part A done already? All right, keep working. Take another minute. So again, treat it like you're foiling. First, outer, inner, last. At this point, replace I squared with -1, which makes that a +6. Okay. So you can add the 12 and the 6 to give you 18, and then you have the multiplier. Joe, step us through. First term gives us? Second term or outer?
Oh. 9i.
-9i, right? Inner?
Positive I.
Last?
6i squared.
Negative or positive?
Negative.
Thank you. That's very important, right?
Yes, it is quite important.
Thank you.
So you get 18 minus I. So you're going to combine the 12 with 6i squared, and you're going to combine the 2 i's in the middle.
Very good. So combine the two i's in the middle as like terms. That gives you the -I. This is really -1. So -1 times -6 gives you this +6. And then the 12 and the 6 combine to give you the 18. Okay, so 18 minus I. Part B. Who wants to step us through part B here? You don't have to have it done. We could do it together. So if you're not done with it, it's fine. But it's 3 minus 5i squared. Pat.
You FOIL it.
Good. Okay, what do we got for the terms?
9 minus 59 minus 59 plus 25i squared.
Okay, good. Continue.
So you get 9 minus 30i, and then that's -1. So
Good.
minus 25.
Very good. And then the 9 minus 25. You're going to have -16 there, right?
Yeah. And minus 39.
Good. And notice everything is in A plus BI form. For part A, 18 was A and -1 was B. For part B, -16 is A and -30 is B. Okay, simple enough. Part C, anybody do it yet and finish? Kate, do you notice anything?
It's difference of 2 squared.
Yes, it is. Take a look at part C, everyone. 5 minus 2i, 5 plus 2i, it's dots. And what happens when you have dots is the middle terms,
They cancel.
they always cancel. Okay? 5 plus and minus 2i, was it?
Yeah.
Okay. So, we'll go through it, but clearly the middle terms are going to cancel. First, we get?
Then first it's 25. It's -10i, positive 10i, and then it's -4i squared.
Okay, cancel the middle terms, please. Make sure the whole thing is gone, including the negative sign there. Kate,
Then it comes out to 25 plus 4.
which is? Okay? So just, you want to make a correlation?
No.
Anybody notice a correlation here between something with radicals? Come on, people. Think back to radicals, last chapter.
What's the difference in two squares? So you have to just square each one, and then when you square the y's, it's negative, so
Okay?
am I?
You're on the right track? No, you're on the right track, but what do you notice similar to radicals? What kind of an answer do we get?
Cube root.
Give me a perfect cube, that would be 27.
Oh.
What do you notice? The last problem didn't have a complex answer. It had a real part and an imaginary part. What do we get?
Just one number.
And what kind of a number? Is it real or imaginary? It's real. Remember with the radicals? If we had 5 plus root 2 and
5 minus root 2.
what did we call them? What was the term for them? What was it?
Binomial conjugate.
Binomial conjugates. Remember that term? 5 plus root 2, 5 minus root 2. When multiplied, that helped us rationalize a binomial irrational denominator. What's going to happen here is the same thing.
Oh, no, we're going to have to rationalize
Okay?
this.
We're not going to have to rationalize, but what we're going to notice is that if we divide by a complex number, it's the same thing as rationalizing, it turns out. But what we call these now are called complex conjugates. Okay, so we can read here. Who can read for me nice and loud? Yes, Joe, go ahead. What was your name? Luis? Nice and loud, Luis.
Notice that the result of part C is a real number. This is because the product in part C is that of complex conjugates. A plus bi and a minus bi, resulting in a squared minus b squared I squared.
Which becomes?
Which becomes a squared plus b squared, similar to binomial conjugates.
Okay, so that's the key here. The middle terms drop off. You end up getting whatever a was squared minus whatever b is squared, and then you have an I squared. The I squared is negative 1, so this becomes just simply negative 1, which makes this a squared plus b squared. And if you go back and you take a look at the last example, we had an answer of 25 plus 4. Well, Kate, you told us the 25 came from 5 squared, right? And the 4 actually came from negative 2 squared, I squared, which became just positive 4. So if you just simply think about it this way, this is what it was really from the last example. Okay? That's where our answer became 29. So whenever you have complex conjugates, just look at a squared plus b squared as your answer. Okay? A squared plus b squared as your answer, as opposed to a squared minus b squared. Remember, a squared minus b squared was our example where dots and binomial radical expressions. But because we have the I squared, the negative b squared becomes a positive b squared in this case. So it doesn't really look like dots, even though it is dots. Okay? So for example, can somebody tell me real quick what this is? Okay? Right away recognize that you have complex conjugates. What's a squared plus b squared going to give us in this problem? What's 4 squared? 3 squared?
20.
3 squared is 20 something?
25.
9. 16 and 9 gives us?
25.
Oh, 25. There it is, Joe. Why don't you answer the question being asked? You have to work on that. You always answer the last question, not the intermediate one. All right, let's go on to the next example now. So what we're going to see for this kind of a problem is that if we actually want to perform division, perform division by multiplying by the complex conjugate of the denominator. So think of this as rationalizing the denominator. Okay? So start by please writing 5 minus 3i over 5 minus 3i.
So we are trying to figure out what the I in the bottom?
Yeah, so to divide with complex numbers, there's no way to divide these two. You can't divide them. They're binomials. But what we can do is multiply by the complex conjugate so that we get a numerical answer in the denominator. And a real numerical answer. Okay? Because this is not in a plus bi form right now. But our answer will be in a plus bi form. Please remember the numerator still needs to be what? What do you have to do to the numerators here? How do you multiply those expressions? Yeah, you still need to FOIL or double distribute the numerator, please. Okay, you still need to FOIL or double distribute that numerator. Joe? It'll become plus.
Yeah, that's what I meant.
I'm not going to show the middle terms in the bottom. I'm just going to put x's in their spots. We don't need the middle terms. They cancel. So yes, Joe, you're going to get 25 plus 9 in the bottom.
Will it always be positive? The result?
Will the result always be positive? In the denominator? Absolutely. Why? Answer your question. Or answer my question now.
Because of the negative 1 in the I squared.
Correct. Very good.
Would this simplify to 1/2 minus 17i or 1/2 minus 1/2i?
The 34 is divisible into both of them, yes.
Okay.
Whenever you have a monomial denominator, it must divide into each term in the polynomial numerator. Okay? So if you had 10 terms in the numerator, you got to divide the 34 into all of them. Okay? Okay, take a look at the work. Make sure you got this. The numerator, when FOILed, you should have had 20 from the first, negative 12i from outer, negative 5i from inner, plus 3i squared from the last part. The I squared is negative 1. So in the numerator, we really have 20 minus 3, because this negative 1 has to be applied. 20 minus 3 gives us this 17 in the very front here. The middle terms, we have negative 12i, negative 5i is negative 17i. All over a denominator. Well, the denominator is 25 minus 9, but the 9 is times negative 1, so this just becomes a plus, really. So this is 25 here, plus 9 is 34. Jared noticed right away that 17 is divisible, or 17 and 34 can be reduced. 17 over 34 is 1/2. 17 over 34 is 1/2. The minus sign carries down, so this is our final solution. And it's in A plus BI form. What's A? And what's B? Chris?
A is 1/2 and B is 1/2. I. Minus negative.
Yeah, there it is. Negative 1/2, okay? B is only the numerical part. It's not the I. So you were right about that part, but don't forget the negative in front of the 1/2. Okay? So positive 1/2 for A, negative 1/2 for B. What I tend to do tonight is go back over my grad school books from engineering and actually show you guys maybe tomorrow what these results would mean in a system. So if you have a positive A value and a negative B value, what kind of a system is it? Okay, is it a stable system? Is it an unstable system? So I'm going to try and look through my notes and see what they are. Okay? I don't know. Is that your guess right now? Unstable?
Yes.
I don't know. So it could be right. Could very well be. Let's take a look at example 4 here. Determine the reciprocal of 7 minus 2i. Okay, we're going to have one more after this. So it's our second to last problem here. We're doing well with time. Determine the reciprocal. Determine the reciprocal. What does reciprocal mean, everybody? Or one person or somebody for this?
The flipped version.
The flip version, okay.
So 1.
Well, what is it currently over, Joe?
1.
It's over 1, so what would the reciprocal look like?
1 over 7 minus 2i.
Yeah.
Great.
So it's 1 minus 7 over 2i.
Then we
But that can't stay like that. It needs to be an A plus BI form. So what do I multiply by?
7 plus 2i.
The complex conjugate over the complex conjugate. This is analogous to when we had a radical in the denominator and we multiplied by the binomial conjugate over the binomial conjugate. The numerator is easy, right? It just repeats itself. 7 plus 2i. The denominator, remember, the middle terms don't matter. Again, the middle terms don't matter when you're using a complex conjugate or a binomial conjugate or if it's just dots in general. And the middle terms do not matter. 7 by 7 gives me 2i times 2i. Okay, so as Joe's noticing already, I squared is negative 1. So you can drop the I squared just like this and make this a positive here. So again, drop the I squared right here and make this a positive instead, because it's negative 1. So we get 7 plus 2I over 53. Am I done? How should I write it?
Well, 7.
What, Joe, go ahead.
753 plus 253 plus I, or just I,
Yeah, times I, if we're going to use an operation, right? So A is 7/53 and B is 2/53. So again, it's 7 over 53. That's a plus sign in the middle, even though it doesn't look like it. Okay? 7 over 53 plus 2 over 53I. Julia.
What's the point of naming them like A and B?
The point of naming A and B is being able to identify the real part as 7/53, the imaginary part as 2/53, then utilizing those two to determine the type of system you'll have in an application. Right now, there is no point of it, no. But I want you to be able to just know that right now the real part is A, and that's 7/53. The imaginary part is B, and that's 2/53. And those have effects on types of issues or later on, if you do study. Yeah, yesterday I did make a point to say that imaginary components or imaginary values are not really used in life if you don't go on to study math, science, or engineering. Okay? It's not going to be used if you're going to be like, say you want to be an English teacher, or say you want to be, I don't know, a poet, or you want to be a historian, or an architect, or not an architect. What's the people that?
Cashew.
Archaeologists, thank you. Archaeologists. I'm like drawing a blank here. Okay? Yeah, you're definitely not going to use it. I'll be honest. You know that, you know? But good question. Let's take a look at the last one here. Try and work it out on your own. We've seen a lot of these kinds of questions already this year where we evaluate functions at certain locations. So we want to know g of x, okay? And we want to know g of 1 plus 3i. Okay, if you have no idea how to start this, raise your hand. I'll come give you a hint. But if you think you know how to start it, please do it. Okay, but if you want to just give me a quick signal if you don't know what to do to start this. Yeah, right first. If you're confused, think about if I asked you, what is g of 2? What you would do is you would plug in a 2 in both locations for x, in the numerator and the denominator. So instead of g of 2, though, you're not plugging a 2 here, you're taking this quantity, 1 plus 3i. There's going to be a good amount of simplification going on. A very good amount. You have to do this problem almost twice if you think about it. You'll see.
It ends at 46.
Thank you, Anna.
It's my screensaver. That's why I know.
Oh, the times, the bus time?
Yeah.
Well, that's smart. So whenever you can just flash and look at it and see what time.
That's the other reason why I have it.
That's really smart.
I don't know. Do I add first? Yeah. And the bottom.
I told her. Wait, I thought you said those.
Yeah.
And you're actually
What's the ones that?
Oh, do you add the ones? Because that would have made my life. Oh, I skipped a step. That's cool.
Because you can't follow.
I see that. I learned that. I skipped the one. I was like, oh, that one doesn't mean anything. It's stupid anyway.
And I'm almost done with concepts. I figured out what was my eating.
Okay, and he gave it to you or he's going to give it to you? So let's take a look at this example now. Still working on it? Alright, I'll give you another minute. Sorry. I'll put the beginning up.
Wait.
I'm writing out all the steps. You don't have to write out every single step. Okay, but this is what your thought process should be. You should have gotten to this point by now. Okay? Should have at least gotten here. Now you have to continue. You're not done at all.
Yes, sir. How?
Yeah. You want to check your answer?
Get an integer answer?
No, you're not going to get an integer answer. Multiply by the complex conjugate in the numerator and denominator. Numerator will become negative 5 minus 12i minus 15i minus 36i squared all over 25 plus 144. I'm going to use the shortcut there because I know it's a squared plus b squared in the denominator. That's what I'm going to get there. The middle terms cancel. Numerator, cross this off, make that a positive 36. 36 minus 5 is 31 minus 27i all over 169. Or 31 over 169 minus 27 over 169i. Can those be reduced? Well, 169 is the square of 13, it turns out. Okay. I don't know if there's anything else that goes into 169.
No.
Does 7 go into 169?
It's not good.
No.
It wasn't working with all
no.
the others.
Yeah, it should not be able to reduce at all. Okay? Take a look and make sure your work makes sense. Again, the denominator here, I don't even write the middle terms out. 5 times 5 is the 25 here, and they're both negative, so it becomes positive. This is going to become minus 144i squared. So just make it a positive 144. Up here, when you have the negative 36i squared, just cross it off and make it a positive 36. So whenever you have an I squared, cross it off, the whole term, and make it the opposite sign. Okay? Any questions on this one? Is it straightforward enough? Okay, your homework tonight is going to be these types of problems. Adding, subtracting, multiplying, dividing, finding the reciprocal, and then evaluating a function at a location. There's also one other problem in there that says, verify that this is the answer to the quadratic equation by checking. So they're going to give you the answer like this. It's not going to be this complicated. And you have to take it and plug it into the quadratic equation. So say it's like 2x squared plus 3x plus 5 equals 0. Plug it in there and get 0 equals 0 to check that it works. It's going to lead us into chapter 7. This is the last section in chapter 6. We're going to start chapter 7 tomorrow. Okay, your homework. You can go ahead and write it down if you'd like to. Okay? I'm going to try and get your problem sets ready for almost tomorrow. I'm going to attempt tonight.
Wait.
Okay.
Graded or the next ones?
I'm going to make, the ones that are grading ahead is actually grading almost done right now. The ones that are due next are not going to be due until the next test date, but I'm going to try and get them to you tomorrow. So you'll have like 3 weeks or 2.5 weeks almost to do it. The next test is not for at least, I think, like almost 2 weeks because we have that big break for President's Weekend. Okay? So I think it's like, yeah, the Thursday or Friday of that week when we get back.
It's Friday.
And we break this Friday.
That's February.
We're off on Friday.
Sorry, you guys, yeah, you're off on Friday. I'm forgetting I'm not. Yeah. So we have teacher day here.
Maybe
Um,
you